right, so we're looking at finishing up the 10.3 to 10.4 notes today. We left off on this problem where it looked like this angle C, was half as big as this central angle, angle A. If we go into this GeoGebra link that I have provided, I can drag things around and see how there is a 2-to-1 ratio between those angles, no matter how I drag it around, whether the angle is acute, obtuse, or even really big. We can see how that relationship continues to hold. So why does it work that way? Why is the measure of an inscribed angle, this angle C down here, 1/2 the measure of the corresponding central angle? Again, angle C is half of angle A. Why is that true? Can we give a deductive, informal proof as to why that's true? As we've done for a lot of these other problems, we're going to need to draw in some extra auxiliary segments. One of those is going to be segment AC, and another one is going to be segment DE. So by drawing in those two segments, it created more triangles. We have a total of 4 triangles in here now. And of these 4 triangles, there are a lot of isosceles triangles. All of the radii of the circle are equal to each other. So AD equals AE equals AC. Those are all the same. So then in this yellow triangle, we have an isosceles triangle, which means that this angle is going to be equal to that angle. And I'll call both of those, X degrees. They do have to be equal to each other. Finishing off this triangle right here, I'll call this angle, how about W? This blue triangle is another isosceles triangle. And I know that these two angles, these two base angles are going to be equal to each other, but they're not necessarily and probably not going to be equal to those two X's. So I'll call this Y degrees and I'll call this Y degrees. So again, that's because of this blue isosceles triangle. Those two angles are going to be equal to each other. And then one more time, we have this other orange isosceles triangle over here. I know that since those two sides are equal, these base angles are equal. So I'll call this Z and call this Z also, because I know those two angles have to be equal to each other. So here's the setup for the problem. We drew in these different radii. We closed off DE to create these 3 different isosceles triangles. And again, the goal here is to find the relationship between W and Y plus Z. I believe that W is twice as big as Y plus Z based off of what I've seen before. Now, to prove this, we're going to look back at some of these triangles, specifically this yellow triangle again. It is a triangle. I know that the sum of the angles in a triangle is always 180 degrees. In other words, because of that yellow triangle, we know that 2x plus W has to be equal to 180 degrees, right? So it's kind of one of those common facts you knew before this class even, but those 3 angles are going to sum up to 180 degrees. Then let's look at this entire triangle. This is a triangle we haven't looked at yet because it's not isosceles. It might be, but it probably isn't. And in that entire gray triangle, those angles are also going to add up to 180 degrees. This one's a little bit messier though, because if I start at this angle over here, little distinction, this is X plus Y for this angle in the upper left. In the bottom, it's going to be Y plus Z. And then our third angle up here is going to be Z plus X. That is all equal to 180 degrees. So I'm just going around the perimeter of this one, taking each of the vertices of that gray triangle in, and all of those angles are going to add up to 180. Simplifying it just a little bit, I noticed that there are 2 X's, there are 2 Y's, and there are 2 Z's. So combining like terms, and we get this equation. There are multiple variables. There's X, Y, Z, and W. So there's 4 variables in this one. I have this equation from the gray. Additionally, there is this equation from that earlier yellow triangle. The good news about connecting these 2 equations is that both of those equations are equal to 180. So using our transitive property, we could say that this 2x plus W is equal to this 2x plus 2y plus 2z, right? They're both equal to 180. So this expression from the left is equal to that expression from the right. Still a pretty big equation. Good news is in this equation, there is a common term on both sides. We can subtract 2x from both sides. It makes it a little bit simpler. And we're left with w is equal to, on the right, 2y plus 2z. Now about that, I could factor the 2 out. 2 goes into both of those terms. And we get this. This is what we've been looking for all along. W, this central angle that we have right here, W is twice as big as y plus z. So like whatever y plus z is, you have to double it, and then you're going to be as big as W. So this is one of the more important formulas we're going to have. It's not an intuitive one by any means, but it is going to be true that this central angle, W, is twice as big as this angle over here, the y plus z together combined. So that's our next one. Let's look at number 5. It says, given segment FG is the diameter of circle B. Okay, so B is the center of the circle. FG is the diameter. I can tell it's a diameter. It's going through the center of the circle. It says put point H on the circle. I put point H down here. I could have put it somewhere like in this upper left-hand corner, somewhere in the lower right-hand corner. It doesn't matter where. I'm going to put a point H somewhere. And then if we draw in segment HG and segment HF, we get another one of these inscribed angles. Again, this is a part of a vocabulary for us. An inscribed angle is an angle that has a vertex on the circle. It's made up of 2 chords. And what I asked you to do is measure the angle measurement for GHF. You don't have your protractors out, but try to eyeball it right now. And how big do you think that angle is? Does it look like a right angle? Does it look like it's 90 degrees? I think so. And if I wanted to check, maybe I could put my angle or my point H somewhere else. Like if I put point H right here, draw in GH, FH, does it still look like a right angle? Or if I put my point H somewhere, let's say like right here, draw in FH, draw in GH, does that still look like a right angle? So as I move this point H around, is it always looking like it's going to be 90 degrees? I think it does. So I didn't actually measure it, but I think it's going to be 90 degrees. So my hypothesis is an inscribed angle measures 90 degrees. An inscribed angle like this angle H measures 90 degrees if and only if the endpoints of the sides of the angle form a diameter. Right, so one of the things we had beginning in this problem is that we were told that FG is a diameter of the circle. And because this is a diameter, and if we trace this inscribed angle to its endpoints, those endpoints make a diameter together. That's going to give us this 90-degree angle regardless. So I could draw any other diameter that I wanted to. So if I drew a diameter like this, put a point right there, draw a segment to those 2 endpoints of that diameter, and that should make this angle 90 degrees. This is another one that's not necessarily quite as obvious, just like the previous one. It's not really obvious that this is going to be true, but it is a very helpful and useful one. Let me go ahead and clean it up and look at the one that we started with. The last theorem that we did was this one where we said an inscribed angle is half as big as the central angle. Well, if I apply that same principle here, here is my inscribed angle. It's supposed to be half as big as that angle. Well, this is a semicircle because it was a diameter. Half of 180 degrees means that this should be 90 degrees. That's why this one works. This is just a specific case of the previous one. It's an important case because 90 degrees is such an important number for us in geometry. All right, so that's number 5. Number 6. Number 6. So again, we're not going to use protractors in this one. It says measure angle JKI, measure angle JLI. Okay, so I don't necessarily know what they are, but let me say that I'm going to kind of eyeball and say, I think maybe this is 38 degrees. So if that angle is 38 degrees, what implications does that have for us? Well, This is an inscribed angle again. An inscribed angle is when the angle or the vertex is on the circle and it's made up of two chords. If I trace the two sides of this angle, trace those two chords to where they end at points J and I. All right, so what does that mean for us? Well, I'm not exactly sure where the center of the circle is. Maybe it's about right here, but that would mean that this arc angle would be 76 degrees. Looks like my approximation is probably off on this one. That angle definitely looks bigger than 76 degrees. But if this is 38, this arc angle is supposed to be twice as big. This central angle, the same thing, is supposed to be twice as big. So once I know this, I double it to get to that one. Now let's go back the other way. You were also asked to find the measurement of angle JLI. Well, if I get rid of those and I look at JLI, I trace one side of the angle, trace the other side of the angle. And this inscribed angle ends at points J and I like the previous one, which means that this inscribed angle over here is half of this arc angle, or that central angle, same thing. So half of 76 means that this would have to be 38 degrees again. So what we've got going on here is this inscribed angle and our initial one, this is what I'm doing in gray now, both end at the same points, which means they're both going to be half of the same thing. So these two angles, the angle K and angle L, must be equal to each other. And I could draw some other inscribed angles also. So like, let's say I start at point J and I go to here. From point I and I go to there, this would be another 38-degree angle. If two inscribed angles have the same endpoints, then the angles are equal. And as far as the reason goes is because they're both half of the same arc angle. So here is our number 6. Number 7, and this is another one that is definitely not intuitive. So like getting that inscribed angle to be half of the central angle, we could measure that. We could look at a lot of cases. But until we proved it, we weren't sure that it was true. And then this is another one where it's not going to be really obvious that something is going to give us a nice equation. To begin with, we have JILK. This is an inscribed quadrilateral. The circle is circumscribed. This quadrilateral is inscribed. Each of the vertices of the quadrilateral are on the circle itself. So we have this inscribed quadrilateral. That has to be the case for this thing to work. And I'm going to look at this angle L right here. Angle L is an inscribed angle. If I were to trace the two sides of that angle to where they intersect the circle, I have this inscribed angle, which is going to be half of that arc angle. So I'm going to put a little note of this. The measure of angle L is 1/2 the measure of arc angle KJI. Right, this is a variation, or it's a case of the inscribed angle being half of the arc angle from before. So that's how I know that this equation is true. And then another thing I'm going to do here is look at this angle J at the top. I'll put a little mark on it. This angle J is another inscribed angle. And if I trace from point J the two sides that make up this angle until we actually hit the circle, I go to point K. Over here, I go to point I. And so we have this arc angle. Using that same reason again, this measure of angle J, this inscribed angle, is 1/2 of the pink one. It's 1/2 the measurement of arc angle KLI. So both of these two equations I have right now are because these are inscribed angles. Notice I took the two angles that are opposite of each other, not any two angles that are adjacent, but I'm taking these opposite angles and I'm looking at how they're related to the entire circle. And together, orange plus pink make up the entire circle. So if I look at this, the measure of arc angle KJI plus the measurement of arc angle KLI. So KJI, the orange, plus KLI, the pink, has to give us a total of 360 degrees. It's the entire circle. Nice equation, true equation. We know there's 360 degrees in a circle. What I'm going to do with this, though, is I'm going to divide both sides by 2. And there's a good reason for this. I'm going to divide both sides by 2 or multiply all of these terms by 1/2, which would give us 1/2 the measurement of angle KJI plus 1/2 the measurement of angle KLI is equal to 180 degrees. In other words, half of the orange plus half of the pink is 180, right? It's not the entire circle, it's half the circle. Why is that a big deal? It goes back up to this earlier connection. If we add these two blue equations together, on the left side, we would get the measure of angle L plus the measure of angle J. And if we add the right sides together, we get 1/2 KJI plus 1/2 KLI, which is the same thing that we have down here, which is equal to 180. So by adding these two blue equations together, on the left side, we get angle L plus angle J. On the right side, we get this expression, which is down here equal to 180. So by a transitive, I know that that is going to be true. Again, not immediately obvious, but this angle L plus this, or excuse me, this angle L plus this angle J equals 180 degrees. So what do we have going on in this one? The opposite angles in an inscribed quadrilateral are supplements. As long as the quadrilateral is inscribed, those opposite angles are always going to be supplements to each other. So another way to use that in this problem is to look at angle K and angle I. Because this is an inscribed quadrilateral, the measure of angle K plus the measure of angle I is also going to be equal to 180 degrees. Angle K is 1/2 of this green. Angle I is 1/2 of the orange. Orange plus green together is 360, so half those angles add up to 180. I don't have to prove this every time I use it. I just know that the opposite angles in an inscribed quadrilateral are always going to add up to 180 degrees.